So thank you, Maren. Um, we are cosmic explorers, so we explain the astrophysical processes of the universe in our computer, or we point the telescope to different places of the sky and try to explain what we see. But sometimes there are things that we cannot explain, and this is a lot of fun, especially for the large surveys that are made with this fantastic telescope, the Jim Emerson telescope. And we have been exploring the Milky Way by for several years, first doing an initial survey and now the big survey. So we put everything together into the VVVx survey. Our data are public, of course. This is an ESO public survey, and you can find some additional information in our webpage. But one of the things that we do is variability. We observe fields repeatedly. And cadence is not great, but we are able to classify objects into interesting objects that we know and love. Variable stars are our distance indicators that help us unveil the three-dimensional structure of our galaxy, for example. But again, there are some things that we don't know what they are. So sometimes you find things, and we put everything that we don't know in a box, and then to look later. But there are sometimes it's interesting to look at those. But before I go into that, I wanted to make a comparison between the Webb and the VVVx. Of course, there is no comparison. I mean, James Webb is so fantastic, so much better. But this is the area of our survey, and this is one tile E1084, where the JWST field is located, one of the first release images. This is our image of the whole tile. I'm going to zoom in, and again, I'm going to zoom in that region, and now you can recognize which image this is. This is our image on top and JWST image on the bottom. We see similar things, but of course, JWST is much better, much higher resolution, much deeper photometry. I'm showing only images because we did the photometry, and it is depressing to show because the Webb images are 4 magnitudes deeper at the same wavelength. But some of the objects marked there are galaxies. The other way. And we see those galaxies. We don't see so well the interstellar medium, but everything that is a point source that bright enough to be detected by us is there. So this is quite nice. And we provide a context for JWST, which that was what the service were supposed to do, find sources to look at. But since I'm talking about galaxies, we map this part of the universe, which is complicated, has been called the zone of avoidance. A few galaxies detected before, and just to mention that we publish a catalog of galaxies in this field with a few catalogs of galaxies, a couple of tens of thousands of galaxies, which are relevant, for example, for gamma ray bursts if they occur in the galactic plane. But another thing I wanted to mention is that our last graduate PhD is Alonso Luna, graduated last month, and this is a PhD thesis number 28. And this month we will have a PhD thesis number 29 of the VV. So this is another product of this large service where there are now 29 more people there with a useless paper in there. But it's very nice. And just to mention the results of his thesis, he looked for hypervelocity stars in the most difficult part of the Milky Way, right in the galactic center. But this is the best part, where you want to look, because this is where they are produced, as predicted by some models. And so the first thing that he did is he selected clamp giants, so they are there. And then he looked for the ones that have a high tangential velocity, so high perpet motion. And then the final step is spectroscopic confirmation. And of course, the initial search was revealed a few candidates that were some were dubious. But let's say if half of them are real, then there is one of these hypervelocity stars per a couple of million stars. So these objects are quite rare, no? But now the new results from that he came up with are a couple of hundred high velocity stars that need follow-up, but some of them have a spectroscopic confirmation. So this is quite nice. But let me go back to the topic of that I advertised, that is, what is this? And these are, strange objects or even serendipitous discoveries that we have made. And it's how do you search for the unexpected? Initially, you look for the extremes, right? The objects that are too blue or too red, or that blow up by several magnitudes, or they have very large motions, like, for example, Alonso's hypervelocity stars. So there are ways to find unexpected things, but it's harder to find something that is undiscoverable, that you don't know that it is there. We came up with this name because we really put the objects that we could not explain in a bag. Most of these in a separate place, and most of these objects turn out to be, glitches or garbage or cosmic rays or whatever, and spikes from the spider that rotates, and if there are two bright stars and they rotate, they create fancy things and ghosts, bad things. But sometimes there are some things that are interesting, and when you find something interesting, who you're going to call? The Ghostbusters, and the Ghostbusters in our teams are Roberto, Valentin, Phil, Lee, and they put our minds together and say, well, what is this? And this is not easy, and the fact is that we discovered them. And for many years, we don't publish them because it needs spectroscopic follow-up, it needs imaging follow-up, it needs a lot of work. And I need to be sure, because I'm standing in front of you and I will say this object is new. And maybe no, you say this object is clearly is that thing. So it's not easy. This is a difficult game. But among these things, some we could explain in the end, or we could propose reasonable explanation. For example, very redundant nova, violently variable QSOs, or extreme dusty novas, or maybe a star that is similar to the Tabby stars or a Mama Jack object, a giant star that blinked. But today I wanted to show you the last one, that is WIT 12. That tells you that we have a dozen that we have worked on seriously, which is an unusual variable that has a light echo. And this WIT 12. This is a discovery image that is from way back 10 years ago, 2012. And this is a KS band image in 2010. Combined with a KS band image 2011, with a KS band image in 2012, and then do an RGB image, and you see things that vary. If you do that, we were looking for supernova light echoes. If you do that, obviously variable stars will appear of different colors, and we find lots of that. But most things are ghosts and reflections and bad things and garbage. But this one was very strange because there was a change in the nebula. It changed its color. It means a change in brightness. Not only the central object, but also the nebula. The central object was easy because it was a variable star. 1500-day period. So it's a long period variable star. Okay, nothing strange there. But the nebula was also changing. And so maybe it's a Mira that is a background Mira that is illuminating a nebula and making it change. But it's not that. It's a very, very extremely bright object and a spectral energy distribution that I'm not showing the models because it doesn't fit very well the models. And also spectral energy distribution is very red, but you have to take with a grain of salt because there are different apertures and nebulosity is not taken into account in some bands. Okay. And but if you look at the near-infrared spectrum, it becomes also interesting that we took last year. It's featureless and steeply rising to the infrared, and some young stellar objects do that. And when we add the additional information from the archives, for example, the WIT light curves, we see the periodic change continue. So this is a long period object, very periodic object. Amplitude changes are reasonable, and but the WIT is nice. I wanted to mention this because it allows to extend the observations for this. We had only 2 cycles, but WIT allowed us to have 1 more cycle, and it keeps doing the same thing. But the interesting thing is that when you look at the nebula itself, one part of the nebula varies in sync. The star increases in brightness, and this part of the nebula increases in brightness. But the other part of the nebula varies out of sync. So when this the central source is brighter, the nebula on this side is fainter. And what is that? And what we think is a light echo, right? The light is you are seeing. If the observer is there, you are seeing directly the light coming to you, and then the light that bounces on the back side of the nebula and then returns to you. And nice thing about this is like light echoes in supernova is that you can dream about building a 3-dimensional picture of the nebula because you know sizes if you know the light echo. So this was what we saw. And I'd like to finish with, again, no comparison with the LSST. LSST is it's a monster compared with VVV. Our area coverage is the green square there compared with all the area that is LSST going to cover. But in the galactic plane, it's going to be fantastic because we will be very complementary. And we will provide long baseline for variability and proper motion. So a couple of projects for the future are the light echoes, right, of supernova in the galactic plane. And also what I like are the search for new globular clusters in the Milky Way. So my summary is that we have a beautiful database that will give us a lot of work for the future on variability, on proper motions, on stellar populations, star clusters, galactic structure, background galaxies, and a lot of other things. Thank you.